I'm here to present four models coming from the project Deep Acoustic Implementation Learning for Multi-Class Disease Detection in basically resource constrained environments. I come from a group bearing a code software engineering machine learning 28. Yeah, so this is basically my process introduction where we're trying to train four models and compare these four deep learning models on the 36 acoustic features extracted from off recordings. So each model represents a different different level of architectural complexity that we are going to dive deep in. Yeah, so our baseline model is the CNN model. That this model basically covers it determines how much diagnostic information can be extracted from the spatial patterns, the acoustic features. Yeah, so we shall see that it takes in the statistics features as input, which the statistics bear or contain 13 MFCC means and standard deviations, spectrocentric bandwidth, role of ZCR and RMS. So they are taking in this input, we shall of course expect an output for a probability score of each of the four classes. So the probability that will be output for these classes should sum up to 1. So here I am having a CNN architecture diagram. So this shows that have input here where we are taking in the 36 features extracted from the audio recordings. So these will then be passed to block one. Block one, there are 64 filters. So and these 64 filters are going to be 64 filters are going to bear a kernel size of 3. So they're going to detect local 3 feature patterns across the sequence. So after that, we in this we shall do a batch normalization to stabilize the training and also then max pooling that will have the sequence. We shall then go to block 2. Block 2, you see that at block 2, the conclusion of block 2, we are doubling the number of filters. So this number of filters are doubled because block 2 deals with the output from block 1. And the combinations, it basically determines it learns second order combinations that are, of course, now the output from block 2 will be a bit larger than the output from block 1, since it's dealing with is again making second order combinations from what was obtained from block 1. So you see that we shall need a large number of filters for this. Then from there we head into the flatten, and the flatten basically collapses the 2D. It collapses the 2D feature and maps it into a 1D vector. Then so that we will discard the position context. Then we shall do dense 128 will dense 128 dense 128 will basically deal with the combination of all the detected patterns, and then we shall also have a dropout of 0.2 at this of 0.4, which will be a bit higher than the dropouts that have been at several levels. So this dropout will basically help in what? Avoiding overfitting, like preventing memorization of the model. Then the probability output per class will at the softmax will be of course, distributed across the four classes. Yeah, and the probabilities of all these four classes should be able to sum up to one. Yeah, so this is just a mathematical grounding showing what I was explaining. You can see the feature extraction, what happens at the block one, the block two, the flattened plus classification scores, and then the probability here. You see that the probability of each class is the score over the summation of the scores from other classes. Then they also get the loss bearing using this method. So here we see that the CNN model is giving us a test accuracy of 77%, a loss of 0.43. And when you come to the classification report, you see that CNN is doing well for COPD and TB, but it is suffering with COVID-19 and the healthy part. So that has also been illustrated using this confusion matrix, where COPD and COPD have a high correlation with that deep blue color, and also TB. TB has a high correlation with TB. See here, COVID-19 and COVID-19 have a relatively low correlation, so that's why they are in lighter colors. Yeah, so this is the plot for accuracy of the validation and the training. So I'll go to the CNN LSTM architecture diagram. CNN LSTM architecture diagram, of course, the LSTM is being built on top. We are just adding the LSTM layer, the long short term memory on top of the CNN. So it also takes in, it also does feature extraction and of course takes in the statistics features. And of course, this now, when you come to the CNN layers, it's just like what I described in CNN. So to, of course, bear the 64 filters and do some pattern combinations using three future pattern combinations. This will then be used as input at the block two, where of course we double the number of filters because we are going to deal with various combinations from what was output from block one. So from there we go to the LSTM layers. At the LSTM layers, we output position by position, maintaining of course, we have to be maintaining a hidden state across the three gates. So you find that at the LSTM layer, we introduce what we call the gate, where we have the gate gate, we have the input gate and the output gate. So with the forget gate, it helps to disregard irrelevant memory. Then input gate, it stores new information. Then the output gate, of course, does controls what passes forward. Yes, then from there, of course, they will head into the dense dropout and then the softmax, where of course we are outputting probabilities for the what for the classes. Yeah, so this is just the mathematical grounding of the model feature extraction, the CNN blocks. This the mathematics behind. You can see the forget gate, disregarding the relevant memory, the input gate stores new information, and then the output gate controls what passes forward. Then our classification scores, of course, are probabilities for the four classes. So this is this test. We have a test accuracy of 71 and a CNN LCM test loss of 0.that. So CNN LCM is also doing well with COPD and TB, and is suffering with COVID-19 and then the SSI. Yeah, that has also been illustrated using this confusion matrix. Yeah, these are plots for accuracy and loss. Yeah, yeah. So training and validation. Yeah, so here with me I have the DNA architecture diagram. The DNA architecture diagram. Of course, it is in such it is in such a style that we take in the 36 features, then go to from dense to 56 neurons to having 208 neurons. then 64 neurons, 32 neurons, and then finally to the 4 neurons coming up to the 4 classes that we have. So at the input layer, of course, we are inputting the 36 features. Now, when we come to the hidden layer one, you see that the 256 neurons are able to what? To see all the 36 features simultaneously. So these ones are able to run broad nonlinear combinations across the features. Yeah, so when you proceed, there's a progressive compression going on where we are compressing the 256 activations into 128, into 128. So here we are building more abstract representation of the acoustic profile. Yeah, so from there you see that progressive compression also occurs when we reach from here. We see that from the 128 we are coming to half of that, which is the 64. Then from there to the 32 and then to the 4 neurons. So this will output the probabilities for these classes. Yeah, so this is the mathematical grounding of the model, which is just in line with what I just described on the architectural diagram. So the model performance, we are bearing the test accuracy 79% with a precision of COPD, doing well for COPD and TB, and also the model suffers with COVID-19 and the hepatitis. So it is the same, just the same information displayed with the confusion matrix here. There is a high correlation between COPD and COPD, and then TB and TB, and then lower correlation with the other cases. Yeah, so these are plots for the accuracy and loss during training and validation. Yeah, so here I come to my fourth model, where whose architectural diagram has been displayed. That's the CNN GRIU architecture. So it is just more like the CNN LSTM layer, but here we are adding the GRIU layer on top of the blocks. So we take in, of course, 36 features. And when we come to the CNN layers, of course, we are going to have still 64 filters. These are going to extract 3 feature patterns from the 36 acoustic features. And then from there, we shall, of course, forward this to the convolutional block 2, where which works on what has been output from block 1. It basically does the secondary bit of combination for combining several patterns from what? From block 1. So that's why you see that we tend to increase the number of filters because the output at this stage will be bigger than what was output at block 1. So from there, we head into the GRIU layers. At the GRIU layers, we of course have at this stage we have only 2 gates where we have reduced the from the 3 gates that were in LCM, but to only what? 2 gates. So 2 gates instead of the 3 gates. So we have the update gate that combines, of course, the forget and the input gate, and then the rest gate, which controls the past memory influence. So here we see that we are going to deal with fewer parameters than what the other model is doing. So which of course prevents overfitting. Then when you go to, of course, the dense and then the dropout, dense dropout of 0.3, avoiding overfitting, dense of 4. Of course, we are coming to the 4 classes, and here we shall, of course, output the probabilities for these 4 classes that will sum up to 1. So this is the mathematical grounding of the model, the feature extraction, the 36 features, and this into a conv1 block, and then of course at the conv1 block, or this one occurs, and then at the GRIU gates, of course, each is a timestamp T. So we have the update gate and the reset gate. So you see that at the update gate, we look at things like how much past memory And then the research, we look at how much past memory to forget. Yeah, so after then the classification score is supposed to be probabilities for this model. So you see that, of course, CNN TRE model is not doing so well. We're having 0.716. That is, of course, approximately 72%. Yeah, uh, actually score, which is a bit low. But we are looking at targets of making it higher. Yeah, as we continue the training. So it is also doing well with COVID and TB, and then suffering with COVID-19 and everything. So just as illustrated by the confusion matrix. So I'd like to appreciate you.